Okay, in this one we've got what's obviously going to be a double angle identity to use because I can see a double angle right there. And when you have some trig functions with double angles and some other ones with single angles, those are not going to mix well. You're going to need to use a double angle identity to simplify this. And the substitution we're going to make is the tangent of 2 omega substitution right here. Okay, so what that means is when I make that substitution, we'll have on the left 2 tangent omega divided by 1 minus tangent squared omega. You should have that memorized by now. And let's just not change anything else for the moment. So that's going to be minus 3 tangent omega equals 0. Okay, so the only change I made is substituting in the double angle tangent identity. And at this point, now we should be free to go solve it as we can. See, these are all tangents. So let's see what we can manage here. This becomes 2 tangent omega 1 minus tangent squared omega equals 3 tangent omega. I moved that 3 tangent to the other side. And now it's a fraction. I don't want it to be a fraction because I can't solve it until it's just a regular single line equation. So I'm going to say 2 tangent omega equals 3 tangent omega times 1 minus tangent squared. Okay, I multiplied both sides of the equation by the denominator. And now I get what? Let's break this multiplication open here. 3 tangent times 1 is just 3 tangent, and minus 3 tangent cubed omega. All right. Now, keep on working with this. I want to factor it. I know that because I have exponents on some of these functions, and I want to get this in factored form. So I'm going to move my 3 tangent cubed over here, so it's positive. I like the high exponents being positive. They're easier to deal with that way. And to get 0 on the other side, so I can factor this, I want to move that 3 tangent omega over also. So I'm going to subtract that. And what I get is minus tangent omega. Once I subtract the 3 from the 2, I get just the minus left. Now I can factor it. So we pull out tangent omega. That's the greatest common factor. And what's left is 3 tangent squared omega minus 1 equals 0. So now we're not done factoring. Let's see, what can we do here? Well, I think at this point we should just go ahead and try to solve this. So tangent omega equals 0. That's one of our solutions. And the other solution is going to be this guy. 3 tangent squared minus 1 equals 0. Now that is going to take a little more work. I get 3 tangent squared equals 1, which means tangent squared equals 1/3, which means tangent equals plus or minus the square root. Remember, I'm the one taking the square root, so I have to do plus or minus. Plus or minus the square root of 1/3, which, if you rewrite it a little bit, turns into plus or minus 1 over the square root of 3. Or if you prefer, you can think about it this way, plus or minus the square root of 3 over 3. Both of those are common ways of representing that value on the unit circle. So we go over to the unit circle and we say, where is tangent equal to 0? That's the first one. Tangent equal to 0. That happens at 0 and at pi. These angles that are right on the x-axis. And what else do we have? We have tangent equals to plus or minus radical 3 over 3. Well, radical 3 over 3, or 1 over radical 3, are these shallow angles. Okay, in here. So this is the picture we've got. We've got 6 angles as part of this solution. Omega equals, and we just start going through the list. 0 and pi were the easy ones. Okay, and then the other angles are those shallow angles, both positive in quadrants 1 and 3, and negative. So let's see, in quadrant 3, that's going to be 7 pi over 6, and negative in quadrants 2 and 4. So that's going to be 5 pi over 6 and 11 pi over 6. Okay, and that gives me the plus and minus radical 3 that I was looking for. All right? Now, you may be looking at an equation that's slightly different in your problem than this one. Sometimes when you're doing a double angle identity, you have to start with something where it's not already a double angle. You have to work your way backwards to get to the double angle identity. And an example in this problem might be right here. See this right here? This is that substitution I made. If you can get your trig equation to look like that in part of it, you can probably substitute it backwards to this. And depending on your equation, that might be useful. Okay, so remember this technique goes both frontwards and backwards.